Welcome back to the Cisco Introduction to Networks lecture series. Today we will be covering Module 12, IPv6 addressing. If you would like to learn about the previous modules, I will leave a link for the playlist in the description and you can go ahead and watch those lectures. In this lecture, we will cover IPv4 related issues, hence why we came up with the IPv6 addressing scheme, the IPv6 address representation, the IPv6 address types, GUA and LLA static configuration, dynamic addressing for IPv6 GUAs, the dynamic addressing for IPv6 LLAs, IPv6 multicast addresses, and the subnet and IPv6 network. IPv4 issues. IPv4 is running out of addresses. I have mentioned this previously on my previous lectures. Unlike IPv6, the IPv4 addresses are limited in number of addresses we can issue. So the IPv6 is the successor to the IPv4. IPv6 has a much larger 128-bit address space. The development of IPv6 included fixes for the IPv4 limitations and some other enhancements. With an increasing internet population, a limited IPv4 address space, the issues with network address translation, and the IoT devices, the time has come to transition into IPv6. As I mentioned before, the IPv4 is pretty much been exhausted and we have been using NAT as a temporary solution for keep going with the IPv4 addresses. Remember, I have described what NAT stands for, a network address translation, and what it does with IPv4 by separating the private IPv4 addresses from the public IPv4 addresses. One of the reasons why we went with that overhead is because we literally ran out of IPv4 global addresses. And the solution right now is to go with the IPv6 addressing scheme with a 128-bit address space. On the right hand side of this screen, you will see the IPv4 exhaustion. In other words, that we are running out of the IPv4s. Like in North America, we are running out around July 2015. And in South America, we are running out in April 2011. And in Europe, we are running out in September 2012, and so on and so forth. We are literally running out of the number of IP addresses we can give out in the IPv4 space. And that's why we came up with the IPv6 scheme. IPv4 and IPv6 coexistence. Both IPv4 and IPv6 will coexist in the near future, and the transition will take several years. I would say transition would take several decades. Like it's probably going to take 1, 2, or 3 decades probably to completely move on to IPv6 addressing schemes. The IETF has created various protocols and tools to help network administrators migrate their network to IPv6. These migration techniques can be divided into 3 categories. They are dual stack, tunneling, and translation. Dual stack, the devices run both IPv4 and IPv6 stacks simultaneously. This is the most common category that you're going to see in your network administration career, especially in 2022, because we are still in the phase of transitioning. And then tunneling is a method of transporting IPv6 packets over IPv4 network. The IPv6 packet is encapsulated inside an IPv4 packet. This is also something that you may see in your field work. Translation is the network address translation 64, which is the NAT64, that allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT. that we have for IPv4. Remember, in IPv4, the reason why we came up with the NAT is because we are running out of public IPv4 addresses, so we need the network address translation between the public and the private IP addresses. And the NAT64 is actually used not because we are running out of IPv6 addresses, but because we are using that NAT64 to communicate between the IPv4 devices and IPv6 devices. This is an important concept for your exam, so just remember that. Note that the tunneling and translations are for transitioning to native IPv6 and should only be used where it is needed. So dual stack, you will see a lot. Tunneling and translation, you see only where it's only needed. The goal should be at the end to use native IPv6 communications from source to destination. IPv6 address representation. The IPv6 addresses are 128 bits in length and written in hexadecimal. IPv6 addresses are not case sensitive and can be written in either lowercase or uppercase. So like for example, if you have like 0db8, this db can be capital, lowercase or uppercase, it doesn't really matter. The preferred format for writing an IPv6 address is, we have a value here and we have two dots like this, and then we have value here and dot and those notations, and then go on from left, read from left to right. With each X consists of 4 hexadecimal values. So when you read from left to right, each of these X's contain 4 hexadecimal values. In IPv6, a hexstat is the unofficial term used to refer to a segment of 16 bits or 4 hexadecimal values. Example of an IPv6 address in the preferred format can be seen here. For example, we have 2001, and then we have a value here, and then we have value here, value here, value here, value here, and each of them are separated with all of this particular notation, which each of these position containing a 4 hexadecimal value. So we're going to look at some rules related to writing down or representing IPv6 addresses. So the first rule is omit leading 0. So this is to help reduce the notation of IPv6 addresses. So by omitting the leading zeros of a address. An example would be if you have a value of 01AB, that can also be represented as 1AB. 09F0 can be represented as 9F0, and so on and so forth. So if you have 00AB, it can be just represented as just AB because the leading two zeros are not needed. This rule only applies to leading zeros and not to trailing zeros, because the trailing zeros do play a part in the value itself. So if you look at the preferred address, we're going to have an IPv6 address example here with 2001 0db8 000 11111 0000 and zeros here and 0 and 20. Now, what we're going to do, we're going to remove the leading zeros based on the rule number 1. So in here, there are no leading zeros because these zeros are in between two numbers. And if you go to the next value, next position, the value has a 0 at the lead. So we're going to remove that and we're going to end up with db8. In here, we have 4 zeros in this position. That means except for that last 0, everything else, the leading zeros, doesn't matter. So we're going to drop all of those zeros and just leave the last 0 there. There are no zeros here. And again, we have the same thing here as here. We have 3 leading zeros at the front, and then we're going to drop all of those 3 zeros and we're going to leave that final last 0 at the end. And same here and same thing here. And in here, we have a leading 0, we have a value, and we have 2 trailing zeros. remember, we cannot drop the trailing zeros. So we're going to drop the leading 0 and then we leave the trailing 0. So we end up with this IPv6 address from the preferred format IPv address. So that's one of the first rule of representing IPv6 addresses, omitting the leading 0. These rules are very important concepts for your Cisco NetAcad exams and Cisco CCNA and CCNP exams. So make sure you understand that. So that's one of the first rules that we do, which is called the omit leading 0. The second rule is double colon rule. In an IPv6 address, the double colon can replace any single contiguous string of one or more 16-bit hex text consist of all zeros. So what does that mean? So that basically means if you have an IPv6 address, in this example we have 2001 db8 CAFE 100001, these zeros can be dropped. So basically a double colon can be replaced any single string of one or more 16-bit hex text consist of all zeros. So because these are all containing zeros, what we can do is we can put two double colons, and we can have 2001 colon db8 colon CAFE colon 1, and now when we come to these three zeros, we're going to put two colons, so double colon, and then we're going to put 1. So we basically drop all of those zeros because it doesn't need to be represented. We know those zeros exist there. The double colon can only be used once within an address. Otherwise, there would be more than one possible resulting address. So what that basically means is if you have another set of zeros like this in the same IPv6 address, you can't just use double zero twice. So you can have a double zero here. If we have a bunch of zeros here, you can have double colon here and a double colon here, because that's going to be, resulting in confusing IPv6 addresses. So it can only be used once. An example here shown with the 2001 db8 000 111 000 000 000 000 What we're going to do, we will drop these values, these 0 values, and use double colon to represent it. So the same preferred IPv6 address format can be represented as 2001 colon db8 colon 0 colon quadruple 1, so 1111. Now we have double colon here and then 200. Remember, we use both rules now, rule number 1 and rule number 2. We drop the leading zeros. For example, 0 db8 is represented by db8, and these 4 zeros is represented by with just a 0. And we also use a rule number 2, which is using the double colon, and we remove those zeros and we put the double colon and then finally 200 by dropping the leading 0. So those are the two rules of representing IPv6 addresses, especially on your papers and documentations, as well as when you are entering into some of the devices, end devices, manually. Typically, we don't actually use a manual entries of IPv6 addresses for end devices. We typically use a DSCP. But if you have to manually enter to a device, you can use this notation to enter it to a device. IPv6 address types. So we have unicast, multicast, and anycast. These are the three types of categories for IPv6 addresses. Unicast uniquely identifies an interface on an IPv6 enabled device. And multicast is used to send a single IPv6 packet to multiple destinations. And anycast is any IPv6 unicast address that can be assigned to multiple devices. A packet sent to an anycast address is routed to the nearest device having that particular address. Note, unlike the IPv4, the IPv6 does not have a broadcast address. However, there is an IPv6 all-node multicast address that essentially act similar to the IPv4 broadcast addresses. IPv6 prefix length. The prefix length is represented in / notation and is used to indicate the network portion of an IPv6 address. The IPv6 prefix length can range from 0 to 128. The recommended IPv6 prefix length for LAN and most other types of networks is /64. So when it's come to the point IPv6 typically use prefix length, it should be /64. That's what the recommended one. So this is actually showing that /64 prefix length. So we have the prefix with the 64 bits and the interface ID with another 64 bit that can be represented with the hexadecimal value on this, the prefix like this, and the interface something like that. Note, it is strongly recommended to use 64-bit interface ID for most networks. This is because the stateless address auto configuration, or SLAC, uses 64 bits for the interface ID. It also makes subnetting easier to create and manage. And in terms of what is SLAC and how it operates, we will go over that in a later lecture and as we move through these slides. Just know that it is part of the IPv6 IP address handling protocols. Types of IPv6 unicast addresses. Unlike IPv4 addresses that have only a single address, IPv6 addresses typically have two unicast addresses. This is a very important concept that you should understand in terms of differences between IPv4 and IPv6. So these two unicast addresses are the global unicast address, or GUA, and link local address, which is LLA. So the global unicast address, or GUA, is similar to the public IPv4 address. These are the global unique internet routable addresses. So these are the IPv6 addresses that are globally available for routing. And then the local, the link local address, or LLA, is similar to what the IPv4 have for link local, which required for every IPv6 enabled device and used to communicate with other devices on the same local link. So LLAs are not routable and are confined to that single link, the single network link, while the global unicast address, GUA, is the globally unique IPv6 addresses that are used for internet routing. So on the right hand side of this page, you can see you have the IPv6 unicast addresses, and we have global unicast and link local. And then we also have the other divisions such as the loopback, unspecified addresses, unique local addresses, and embedded IPv4. So these are the divisions that we have within the IPv6 unicast addresses. For your exams, you should be able to define GUA, LLA, and how that is differ from the IPv4 and what are the items that we use in IPv4. If you are interested in the IPv4 addressing scheme, please go and check my video or lecture on the IPv4 addressing scheme that I have posted previously. That will give you an idea about the information you need to know about the IPv4 addressing. A note about unique local addresses. The IPv6 unique local addresses range from FC00:7 to FDFF:7, have some similarity to RFC1918 private address for IPv4. However, there are significant differences. A unique local addresses are used for local addressing within a site or between a limited number of sites. A unique local addresses can be used for devices that will never need to access another network. The unique local addresses are not globally routed or translated to a global IPv6 address. So you should know these key features of the IPv6 unique local addresses. So they are used for local addressing within a site or between limited number of sites. They are never needed. They were used for devices that never need access to the another network. So they are like isolated devices. And these unique local addresses are not globally routed or translated to a global IPv6 address. So those are the three key features that you should know about the unique local addresses. Please note, many sites use the private nature of RFC 1918 addresses to attempt to secure or hide their network from potential security risk. This was never intended use of the ULA. So as I mentioned before, you can isolate devices using those unique local addresses, but the intention of the ULA is not to use as a security method, but rather for these particular requirements. IPv6 GUA or Global Unicast Addresses. The IPv6 Global Unicast addresses are globally unique and routable on the IPv6 Internet. In other words, this is the address that can be used to connect global networks. Currently, only GUAs with the first 3 bits of 001 or 2000:3 are being assigned. Currently available GUAs begins with a decimal 2 or a 3. This is only 1/8 of the total available IPv6 address space. So on a Cisco NetAcad CCNA or CCNP exam, this is a question that you might get, because I got this question on my exam, that they will give you an IP address for IPv6 on a multiple choice and ask which of these IPv6 addresses are considered as global unicast addresses. The way you remember this for your exams is that currently only GUAs with the first 3 bits of 001 or 2000:3 are being assigned, and if you see that value in the one of the answers for your exams, and that's what you should be picking. And you should also know, currently we only have assigned 1/8 of the total available IPv6 address space allocated to these GUAs for global IPv6 routing. And this diagram below is just basically showing that in the graphical format. IPv6 GUA structure. There are 3 parts to IPv6 GUA structure: global routing prefix, subnet ID, and interface ID. The global routing prefix is the prefix or network portion of the address that is assigned by the provider, such as an ISP, to a customer or the site. The global routing prefix will vary depending on the ISP policies. Subnet ID field is the area between the global routing prefix and the interface ID. The subnet ID is used by an organization to identify subnets within its site. Interface ID basically is the IPv6 interface ID that is equivalent to the host portion of an IPv4 address. You know how in an IPv4 address, the last octet is acting as the host portion. In IPv6 addresses, the interface ID is pretty much doing the similar thing as the host portion of the IPv4 address. And it is strongly recommended that in most cases use /64 subnets to be used as interface IDs in IPv6 addressing scheme, which will create a 64-bit interface ID. For your Cisco CCNA, CCNP exams, you should know these terms and what they actually mean, so that you will be able to have a better idea about how the IPv6 GUA structure works. Note, IPv6 allows the all zeros and all ones host addresses that can be assigned to a device. The all zeros address is reserved as a subnet router, anycast address, and should be assigned only to routers. So that's a key thing that you should also know. IPv6 LLA. An IPv6 link local address, or LLA, enables a device to communicate with other IPv6 enabled devices on the same link and only on that link. This same link or only on that link can be also described as a subnet. Packets with a source or destination LLA cannot be routed. Every IPv6 enabled network interface must have an LLA, a link local address. If an LLA is not configured manually on an interface, the device will automatically create one. And the IPv6 LLAs are in the FE80:10 range. And in the diagram below right here is describing how LLA works. So the router uses the LLA of neighbor routers to send routing updates. So the LLAs are used between the neighbor router and the routers. And the host use the LLA of a local router as the default gateway. So when we have two routers communicating between each other using routing protocols, the LLAs of the neighbor routers are used to send those updates between the two routers, and the host will use the LLA of a local router as their default gateway. GUA and LLA static configuration. Static GUA configuration on a router. Most IPv6 configuration and verification commands in Cisco IOS are similar to their IPv4 counterparts. In many cases, the only difference is the use of IPv6 in place of IP within the commands. So that's what is showing on here on the bottom of your screen. I will do a live demonstration of Cisco Labs with IPv6 and how you can assign IPv6 addresses, so that you will have a better idea of what exactly this slide is talking about. But here what you need to understand is the command to configure an IPv6 GUA on an interface is just IPv6, and then you put the IPv6 address, and then you put the IPv6 address / the prefix length. For example, in this example we have IPv6 address, so that's the command, IPv6 address, and then we're gonna put the address here and / whatever the prefix length in this here is the 64. So that's what this example is showing, and this particular command, this particular IP address is being entered into the interface gigabit 000 because we are in the configuration of that particular interface. And issuing the no shutdown command, we basically put this interface into back onto online with that IPv6 address. Manually configuring IPv6 address on a host is similar to how we manually configure an IPv4 address. The GUA or LLA of the router interface can be used as the default gateway. So in here, the default gateway is the GUA or the LLA of the router interface. Just like in IPv4 addresses where you put the default gateway as the interface of your router, we use the GUA or LLA of the router interface for IPv6 default gateway. The best practice is to use the LLA, but you can use either one, that should work. when DHCP v6 or SLAC is used, the LLA of the router will automatically be specified as the default gateway address. So we can use either GUA or LLA when you're manually configuring it, but if you are using the DHCP IPv6 address, it will always be the LLA address that will be assigned as the default gateway. If you look at the right hand side of your screen, this diagram basically showing that manually entering it. One of the key difference here I would like to point out to anybody who is studying for these classes is that in IPv4, you had to enter this entire subnet prefix, but here we just put the subnet prefix length, which is 64. Remember, if this is IPv4, we'll be entering like 255.255.2550, for example. In here, instead of putting the /24 or something, /36 or etc., in here, we just put the prefix length, which is 64. This is made that way so that it is easy for humans like you and me to do network configurations. Configuring the LLAs manually lets you create an address that is recognizable and easier to remember. LLAs can be configured manually using the IPv6 address by entering IPv6 address and then the link local address, and then put link local command, and then that will give you the LLA assigned within your Cisco router. So in Cisco ISO devices, the ISO software firmware, this is an example where we assign an LLA to the port, the interface G000 on R1, the router 1. So just like before, we enter the configuration mode of that port and we give IPv6 address. This is the command IPv6 address, and then we give that link local address, and then we enter the command link local right behind it and press enter. And then by putting it into no shutdown command, what we do actually, we put this interface online with this particular LLA address. Note the same LLA can be configured on each link as long as it is unique on that link. So that's a very important concept. The same LLA can be configured on each link as long as it is unique on that particular link. Common practice is to create a different LLA on each interface of the router to make it easier to identify router and specific interfaces. So if you have different interfaces, it is common to create different LLAs for each interface. So if you go to Gigabit Ethernet 001, for example, you will create another the LLA value for your link local so that it is unique for that each interface of that router. Dynamic addressing for IPv6 GUAs. RS and RA messages. RS is the router solicitation and RA is router advertisement. Devices obtain GUA addresses dynamically through Internet Control Message Protocol version 6, which is known as ICMPv6 messages. Router solicitation or RS messages are sent by host devices to discover IPv6 routers, while router advertisement or RA messages are sent by routers to inform host on how to obtain an IPv6 GUA and provide useful network information such as network prefix and prefix length, default gateway address, DNS address, and domain name. The RA can provide three methods for configuring an IPv6 GUA. Those are SLAC with stateless DHCP v6 server, and stateful DHCP v6 server which doesn't have the SLAC. For this particular course, you just need to know what RS and RA, how they are differ from each other, and how each of them can provide different services within this IPv6 system. in my future courses, we will go into depth of RS and RA. So for now, we're just gonna brush the surface of these concepts. Dynamic addressing for IPv6 GUAs, the method 1, which is SLAC. So SLAC allows a device to configure a GUA without the services of a DHCP version 6. Devices obtain the necessary information to configure GUA from the ICMP version 6 RA messages of the local router. The prefix is provided by the RA, and the device uses either EUI-64 or random generation method to create an interface ID. So this is an important concept. So the prefix is provided by the RA, and the device can create device can use either the EUI-64 or random generation method to create an interface ID. So either one would work. And this is what is shown in the diagram here. So you get a message from the RA with the prefix on it and the interface ID either created by the client device itself using the EUI-64 EUI-64 configuration method or random 64-bit number. The second method is SLAC and stateless DHCP. How that's going to work is an RA can instruct a device to use both SLAC and stateless DHCP version 6. The RA message suggests devices use the following. It'll give the SLAC to create its own IPv6 GUA, the router LLA, which is the RA source of IPv6 address as the default gateway address, and a stateless DHCP version 6 server to obtain other information such as DNS server address and the domain name. So the diagram here describes how the process for SLAC and stateless DHCP works. So we have a RS message sent from your device to the router, and the router send an RA message back to the device with the DHCP version 6 information, the server information, and then the device that information get forwarded to that stateless DHCP version 6 server, and that's how the device going to obtain the information needed to connect to the network. The third method is the stateful DHCP version 6. An RA can instruct a device to use stateful DHCP version 6 only. In stateful DHCP version 6, what happens is it is very similar to GSCP for IPv4. A device can automatically receive a GUA, prefix length, and the address of the DNS servers from a stateful DHCP version 6 server. The RA message suggests devices use the following. The router LLA, which is the RA source of the IPv6 address for the global gateway address, a stateful DHCP v6 server to obtain a GUA, DNS server address, domain name, and other necessary information. And on the bottom of the screen, it is visually describing how the stateful DHCP version 6 work. So you have your device trying to connect to the network. It sends a RS message and it goes into the router, and router send the RA message back, and it'll go and solicit the DHCP version 6. And that's how it's gonna get all the information necessary to connect to the network. EUI-64 process versus random generated. On my previous slide, we briefly brushed over what EUI-64 and random generation, but we didn't go into depth, and here we're going to explain that a little bit in more detail. But again, we are not going into too much detail for this in this class, but this is all you need to know. So when the RA message is either SLAC or SLAC with stateless DHCP version 6, the client must generate its own interface ID. The interface ID can be created using two methods, either EUI/64 process or randomly generated 64-bit number. So how it's going to work is basically we have a ICMP-v6 router advertisement, and it goes to your end device, and the end device has to use that message, RA message as the prefix, and then create that interface ID randomly so that it is unique to this particular device and connect to the network. So we're going to look at it in a little bit more detail about how EUI/64 work now. EUI/64 process. The IEEE defined the Extended Unique Identifier, or EUI, which is a modified version of the EUI/64 process that performs the following. A 16-bit value of FFFE, which in hexadecimal, is inserted into the middle of the 48-bit Ethernet MAC address of the client. The 7th bit of the client MAC address is reversed from the binary 0 to 1. And that's how you get the EUI/64 process to obtain that particular value. So in this example, we have a 48-bit MAC address, and that would be FC 994775CE0. And the EUI/64 interface ID use that 48-bit MAC address and use these principles above to generate that interface ID. So it uses that MAC address and it takes FC and convert that into FE, and it takes this this value. They insert these two values, FF and FE, to generate that unique interface ID. So this is an important concept that you understand and how it works for your exam. So if you would like to have a summary, you can come back to this slide for your exams and quizzes. Next, we're going to look at the other method, which is the randomly generated interface IDs. So how it works is, depending on the operating system, a device may use a random generated interface ID instead of using the MAC address and the EUI/64 process. So beginning with the Windows Vista, Windows uses a randomly generated interface ID instead of one created by EUI/64. So if you are using any Windows computers, starting from Windows Vista all the way to now Windows 11, they all will be using the randomly generated interface ID. And if you go to your Windows computer and you go into command prompt, and if you type ipconfig, and the IPv6 address information that is showing up on your command prompt is actually created using the random generated interface IDs. Note, to ensure the uniqueness of any IPv6 unicast address, the client may use a process known as duplicate address detection, or DAD. So this is very similar to an ARP request for its own addresses. If there is no reply and then the address is unique. So what's going to happen is, in this case, when the randomly generated address is created by the Windows machine, it's going to use the DAD, duplicate address detection process, to make sure that this address is unique within that network. And if it is not unique, what's going to happen is it's going to generate a new address until it is absolutely sure that there are no duplicate addresses within that network. Dynamic addressing for IPv6 LLAs. Dynamic LLAs are all IPv4 interfaces must have them. So all IPv6 interfaces will have an LLA associated with it. Like IPv6 GUAs, LLAs can be configured dynamically. The figure shows the LLA is dynamically created using FE80 /10 prefix and the interface ID using EUI-64 process or randomly generated 64-bit number. So we have the FE80 /10. So that's the prefix right here, and we are using 64-bit value at the interface interface ID right down here. So this is just diagram is just summarizing what is described above here. So that's how the dynamic LLAs work. Dynamic LLAs on Windows. Operating systems such as Windows will typically use the same method for both Slack created GUA and a dynamically assigned LLAs. So the EUI-64 generated interface ID look like this, and then the random 64-bit generated ID look like that. You don't need to know how to identify them on an exam, because there's no such thing as like just identifying them between the two. But just remember, there's EUI-64 generated interface ID and random 64-bit generated interface ID both exist in IPv4 configurations. Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. By default, Cisco iOS routers use EUI-64 to generate the interface ID for all LLAs and IPv6 interfaces. So this is an important concept that might show up on your CCNA and CCNP exam. I got this question asking, what is the default of Cisco ISO routers? And by default, all Cisco iOS routers use the EUI-64 to generate the interface ID. So you should know that. And in here on the bottom of the screen is an example of LLA dynamically configured on this particular interface, Gigabit Ethernet 000 on a R1 router. Again, you can pause this video if you want to have a look at it. But what's important is not that you understand how these things work in detail, these numbers. What you need to know is how to identify those numbers on a Cisco router if they give you this image, or to and also to understand that the Cisco ISO routers currently use EUI-64 by default to generate those IDs. That's the important thing you need to get out of this slide. Verify IPv6 address configuration. On a Cisco ISO device, what you can do, actually, you can run the show interface Gigabit Ethernet 000 or show interface, whatever the interface you're gonna have on your router. It doesn't need to be Gigabit Ethernet 000, whatever the interface you want to look at, and that will show you the information related to that IPv6 configurations. So if there's an IPv6 configuration attached to that Cisco router, you should be able to look that information up by just going through that process. The other command that you should know is the show IPv6 interface brief. That will also give you some additional information about the configurations, the same information actually with the configuration related to that IPv6. So that's what this slide trying to get you, and the information about here is the same as the previous slide. There's a packet tracer lab available to you on your Cisco NetAcad. If you have access to Cisco NetAcad, and go ahead and do it, and it will explain how you can configure IPv6 addresses and test and verify those network connectivity. The lab is titled Configure IPv6 Addressing, and if I get hold of these labs, I will post them on my website so that you have access to them. If you have access to your Cisco NetAcad, you can go ahead and do them. IPv6 multicast addresses. Assign IPv6 multicast addresses. IPv6 multicast addresses have the prefix of FF00::/8. there are two types of IPv6 multicast addresses. Well-known multicast addresses, solicited node multicast addresses. Multicast addresses can only be destination addresses and not the source addresses. So those are very important concepts. So there are two types of IPv6 multicast addresses, well-known multicast addresses and solicited node multicast addresses. And the multicast addresses can only be destination addresses and not the source addresses. Well-known IPv6 multicast addresses. A well-known IPv6 multicast addresses are assigned and are reserved for predefined groups of devices. And there are two common IPv6 assigned multicast groups. They are all nodes multicast group and all routers multicast group. The all nodes multicast group is associated with FF02::1, and this is a multicast group that all IPv6 enabled devices join. A packet sent to this group is received and processed by all IPv6 interfaces on the link or the network. The FF02::2, which is associated with all routers multicast group, and this is a multicast group that all IPv6 routers join. A router becomes a member of this group when it is enabled as an IPv6 router with the IPv6 unicast routing global configuration command. And these are two important things that you should know about the two common IPv6 assigned multicast groups. So let's look at the solicited node IPv6 multicast. A solicited node multicast address is similar to the all nodes multicast address. A solicited node multicast address is mapped to a special Ethernet multicast address. The Ethernet network interface card can filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the device is the intended target of the IPv6 packet. So basically it's increased the efficiency. So the Ethernet network interface card can filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the device is the intended target of the IPv6 packet. And this is what they are trying to explain here with this particular diagram on the right hand side. I'm not going to go over it into detail. You can pause this video if you would like to look at it. There's a lab available to you on your Cisco NetAcad called Identify IPv6 Address. If you have access to this particular lab through your Cisco NetAcad, go ahead and do it. And if you don't, I will try to obtain a copy of this lab and post it on my website. So you can go ahead there and do it. I would recommend doing these labs as you go through these modules so that you have a better idea of all the concepts that we were going to cover. Subnet and IPv6 network. Subnet using the subnet ID. IPv6 was designed with subnetting in mind. A separate subnet ID field in the IPv6 GUA is used to create subnets. The subnet ID field is the area between the global routing prefix and the interface ID. So we have the global routing prefix here and the subnet ID with the 16-bit in the middle, and we have the interface ID behind it. So we have 48 bits for the global routing prefix, and we have 16-bit for the subnet ID and the 64-bit for the interface ID. Like in here, a 48 routing prefix plus 16-bit subnet ID equal to 64 bits prefix. So that's how it gives you the 64 prefix up here. That includes the subnet ID. Given the 2001 ACAD:/48 global routing prefix with a 16-bit subnet ID, we can allow 65,536/64 subnets. The global routing prefix is the same for all subnets, and only the subnet ID hex text is incremented in the hexadecimal for each subnet. So that's what is showing on the right hand side of the screen here. And again, I'm not going to go through this in detail. In this particular course also, you should realize that you don't need to know exactly how everything works with subnetting with respect to IPv6, but you should know how to subnet IPv4. So that's another important thing about this course. IPv6 subnet allocation. The example topology requires 5 subnets, one for each LAN, as well as for the serial link between R1 and R2. So this is the topology that we have down here. So we have a serial link between R1 and R2, and then we have 5 subnet, 1, 2, 3, 4, and plus this one, right? So the 5 IPv6 subnets were allocated with the subnet ID field 001 through 005. Each with /64 subnet will provide more addresses than will ever be needed. So that is shown here on the right hand side right here with this diagram with respect to the left hand side topology we have here. Router configured with IPv6 subnets. The example shows that each of the router interfaces on R1 has been configured to be on a different IPv6 subnet. So if you look at this example here, we have a R1, the router 1, and this Cisco iOS device. We have the interface 000 here, and it has a particular IPv6 subnet, and then the next interface have a different IPv6 subnet, and the next one has a different IPv subnet. See, 1, 2, 3 is actually changing. So that's what it's shown here. For your module quiz and exams, all you need to know is that basically, you know, how to identify different subnets by just looking at this sometimes, but you don't need to know in detail exactly everything to go with IPv6 subnetting for this particular module, but you should know the IPv4 as I mentioned before. What did we learn in this lecture? There are several packet tracer files and lab files available to you on your Cisco NetAcad that will cover everything we covered in this particular lecture. But if you do not have access to those labs or NetAcad, I will see if I can get a copies of them and post it on my website so you can go ahead and do them. And if you do have access to it, it is called the Implement a Subnetted IPv6 Addressing Scheme, and that will go over everything we just covered. Again, there is a lab called Configure IPv6 Addresses on Network Devices that will also cover some of the topics that we covered in this particular lecture. If you have access to them, I would highly recommend doing them because it will encompass everything that we just covered. So let's look at a summary of everything we learned in this lecture. We learned IPv4 has a theoretical maximum of 4.3 billion addresses. Hence, we are actually running out of those IPv4 addresses. The IETF has created various protocols and tools to help network administrators migrate their networks to IPv6. The migration techniques can be divided into 3 categories: dual stack, tunneling, and translation. And remember, I mentioned the dual stack is something that you probably going to see, most likely going to see in the field in 2022, as we are in the transition phase of the IPv4 to IPv6. Also, I believe that this is going to take several decades for us to completely transfer into IPv6 from IPv4. IPv6 addresses are 128 bits in length and written as a string of hexadecimal values. The preferred format for writing IPv6 address is shown here with those colons separating each of these positional values. With each X consists of a 4 hexadecimal value. So each of these X represent 4 hexadecimal values. There are 3 types of IPv6 addresses. Those are unicast, multicast, and anycast, and you should be able to describe them and how they are different from each other. An IPv6 unicast address uniquely identifies an interface on an IPv6 enabled device. IPv6 global unicast addresses, known as GUAs, are globally unique and routable on IPv6 internet. And IPv6 linked local addresses, such as known as LLAs, enable a device to communicate with other IPv6 enabled devices on the same link and only on that link, which can be considered as a subnet. The command to configure an IPv6 GUA on an interface is IPv6 address on a Cisco iOS device. And then after that command, IPv6 address, you can enter the IPv6 address / the prefix length, and that will allow you to configure the IPv6 GUA on a Cisco device. A device obtains a GUA dynamically through ICMP version 6 messages. IP version 6 routers periodically send out ICMP version 6 router advertisement messages or RA messages every 200 seconds or so to all IPv6 enabled devices on the network. So remember that. A device obtains a GUA dynamically through ICMP v6 messages, and IPv6 routers periodically send out ICMP version 6 RA messages every 200 seconds to all IPv6 enabled devices on the network. RA messages have 3 methods: Slack with stateless DHCP version 6 server, and stateful DHCP version 6 with no Slack. You should know how each one of these things works in general for your exams and quizzes. The interface ID can be created using the EUI-64 process or randomly generate a 64-bit number. The EUI's process uses the 48-bit Ethernet MAC address of the client and insert another 16-bit in the middle of the MAC address to create a 64-bit interface ID. Depending upon the operating system, a device may use a randomly generated interface ID or may use the EUI-64 method. All IPv6 devices must have an IPv6 LLA. An LLA can be configured manually or created dynamically. Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. That is an important concept that may show up on your CCNA, CCNP exams. Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. There are 2 types of IPv6 multicast addresses. Those are well-known multicast addresses and solicited node multicast addresses. 2 common IPv6 assigned multicast groups are, remember, FF02:1 and FF02:2. And the FF02:1 is associated with all node multicast group, which are used by devices, while the FF02:2 is used by all routers with in that multicast group. A solicited node multicast address is similar to the all nodes multicast address. The advantage of a solicited node multicast address is that it is mapped to a special Ethernet multicast address. IPv6 was designed with subnetting in mind. A separate subnet ID field in the IPv6 GUA is used to create those subnets. But however, as I mentioned before, unlike IPv4 subnetting, we are not going to do a lot of IPv6 subnetting in this particular course. And that will bring us to the end of this lecture. If you have any questions related to this particular lecture, you are more than welcome to leave a comment below, and I will try to get back to you as soon as possible. If you would like to watch my previous lectures, I will leave a link in the description to the playlist for the Cisco NetAcat Introduction to Networks lecture series. Please thumbs up this video and subscribe to this channel if you are interested in more videos like this. And until our next lecture, good luck with your exam and have a nice day.